Example for class 20. We call this example 2. It's problems 875 from Shigley. The vertical channel, of 152 by 76 from table A7, you see in the appendix, has a cantilever beam bolted to it as shown. The channel is hot rolled AI-SI 1006 steel. The bar is hot rolled AI-SI 1015 steel, and the shoulder bolts are M10s by 1.5 ISO 5.8. That's the grade. For a design factor of 2, find the safe static force that can be applied to the cantilever. You will need to check 6 possible failure modes. Okay. Well, I already have this written out, so I'm going to go step by step through it here. Notice that this is 12 millimeters thick. We might need to go up and find what the thickness is of this vertical channel so that we could evaluate that. We might actually need to look up material properties so we could get over that. We want to look up what the bolt properties are, the ISO 5.8. So there's a number of things that we could do to start off. So we look up at the bolts and we find the yield strength is 420 megapascals, and we might as well turn that into shear yield strength. And then we look up the channel we look up the material from table A20, and we get 170 megapascals for that kind of steel. And from A7, we look up that the thickness through the web, it's the web thickness we want, is 6.4 millimeters. And the cantilever, we look up, again, the material from A20, and we find it has 190 megapascals, which we can convert into shear by multiplying by 0.577. And, okay, so now we start distributing the loads. We could find the F prime by taking the load that we'll eventually get and dividing it by 3. We could find the moment by multiplying to the bolt center, which we carefully check and see that each of the dimensions they add, so we end up with 201. And so now we've applied these loads, and we'll see that the primes are going downwards, but the FC double prime is going downwards on the right. FA double prime is going upwards. We've already kind of walked through a little bit of this example, but you can look through there. So if we apply, and what they've done right here is they've kind of oversimplified this right here. But what they did is they took M, right? So this is F double prime, right? N is equal to M times Rn times like the sum of all the Ri's squared, like this individual ones, right? But for here, we had, this was the distance, we'll call this like R, and you know that they're equal to each other, so it might as well just be R. It doesn't matter, it's all the R's there are. And so we add that 201 F is what the moment is. That's what we calculate the moment to be. And then, well, we would multiply that by R, but then we would sum up all the R's. Well, there's only going to be this one R and this other R, and they're going to be R squared. So we go 2R squared. So you could see that the R's cancel out. So that's how we were able to get, we would plug in 50 for the R, where it's a little I guess, they're showing the geometry right there. So that's why they do this abbreviated piece right here. This is a cut and paste of sorts. I modified it somewhat from the solution manual. So we can find out what the max force is going to be at C, right? It's going to be located right here because that's where the primary and the secondary, where they add together. And we don't have to mess around with angles because it's a simple problem. So now we start going through the different things that could break. And we look at the bolts, and they could shear off based on this maximum load that's possible. So we get this shear area at 78.54 millimeters squared. And so I just put a little picture over here to show that's the way that it's going to fail. And so we write out the equation that this tau is equal to FC over AS. And when we have that's going to be we set that equal to the allowable. So the maximum is equal to the allowable. The allowable is the strength divided by the safety factor. And using that force that we get up above, we're able to rearrange this equation right here, solving for force, and we end up with 4.06 kilonewtons. And so that's the limiting force that we can apply at the end right here to not shear off that bolt C. For bearing on the bolt, we take the bearing area and we take the worst case, right? So the worst case is going to be at the thinner part. That's where the higher bearing stress is going to be. So we take, this is the flange, or excuse me, the web of the cantilever is that thickness, and multiplied by the bolt diameter, we get this area, and it's going to look like this right here. So that's the place, that's the spot where the bolt would be dented. I'd actually, I might argue with that. In hindsight, I bet it would be up above, right? Doesn't that make sense? That the top of the thing would be being pressed down against it. And in a similar manner, I guess that's what they mean is similar to shear, that we write that sigma is going to be the FC over this bearing area, SY divided by N. We might call that an ND because it becomes a design factor here. So that you'll see when we rearrange this right here, we've really just, and we've taken out this guy right here, this coefficient in front of the F. So we're able to find what F is, and we see that it takes more to hurt the bolt by way of bearing stress than it did to shear the bolt off. And then bearing on the channel, well, that really should be the same area, right? It's going to have a different strength, though. And so we go that route right here. Almost everything's the same, excuse me, except that the strength is going to be different, right? The strengths are different here. So we get a lower. So far that's the controlling condition in terms of if we specify that we can't allow to have damage to the bolt of any sort. Now continuing, and we want bearing on the cantilever now instead, right? So this right here, what we just did, that was on the channel. Now we want to check the cantilever, but it has a different thickness. Remember, it's 12 millimeters thick. So it has a different bearing area. It's 12 times 10, the bolt diameter. And it has a different strength. So I'm showing it right here again. I think it should be like up at the top once again. It's going to be now the channel that's going to, not the channel, but the member, the cantilever bar is what they mean, the pink guy. And we rewrite this out, and most of the things stay the same except for the strength and the, excuse me, and the area was different from us, so we get 4.87. So still, this guy wins out right here. He's still the most. And now we go bending of the cantilever, and we can get the moment of inertia by subtracting out the whole part of the thing, right? So what we're trying to find the area moment of inertia of a cross section that looks like this right here, right? Because we got this hole. Easier to do than maybe I did discuss maybe too long in the lecture portion how you would go about getting the moment of inertia when there was only one hole and it was off-centered. It's just a little bit more work in the parallel axis theory. This is pretty easy because it's just I of the big rectangle minus I of the small rectangle, and everything's the same except for the BH cubed over 12. The H cubed is different between, here's the total amount and here's the bolt. So that's why we have this as the area moment of inertia. And we know that the stress is equal to MC over I, but it also needs to be equal to the allowable stress. So rewriting that thing out, we're able to figure out what the force is on there, and we get 3.12. So that's the maximum allowable force so that we don't bend. And then lastly, we have shear of the cantilever, right? So that's going to be looking like these two straight. Now that is the place I think that the thing is going to rip out right here. And the area is going to be 2 times the distance away from the edge. And they're saying 25, and I would argue with you that you should instead, so this is probably kind of old, but I think that you should, that's halfway right here. I say that you should use this dimension right there, right? So it's going to give it a much more chance right here. So this is 25, but it would be 25 minus 6. So this would be 19. So I think that this should be 19 personally. But let's see what that would come out to. It's also going to be shear, so we want to use the shear strength, but it's going to be the cantilever. The same thing is not going to happen to the channel. That's important, right? You can't shear out from the channel. You can make the hole bigger from the bearing, but you can't really fail it in shear. But this one, this member, this cantilever, it could shear. So we rewrite out this thing, and for the maximum stress, set that equal to the allowable stress, and we have our FC over the shear area there. And we end up, it's going to take 14 kilonewtons. So that was totally safe. We can go back and try to look at it. I would say instead that we'd go 19, 2 times, 12 times, so that this guy, he reduces to 456. And so if we were to plug that in there, so that's times 109.6 times, and then 2 divide, and then 2.343 and divide. And I think what you end up with is instead you would get a 10.67 kilonewtons. So by far we're okay. So the answer is the limiting load should be 2.32 kilonewtons based on the bearing on the channel. So that's an analysis of here where we're trying to pick through all the different types of stresses and failure modes that could possibly happen. And I'll discard all this stuff. And I think I already did this use the guitar in class, but I like this guitar a whole lot. And so why don't we put him back into play? This is the Gibson ES335. This is not an old one, but it looks like an old one because it has Seymour Duncan Antiquities in it. They're all rusted and corroded, but they make them out of old material and cloth wire covering, and I don't know if any of that affects the sound at all. Probably not at all. I mean, it's very unlikely, right? So this is very much a classic blues guitar, right? B.B. King played a similar model. His was actually, I think it is a 355. It's got different hardware, and I think it even was like a particular. His name is Lucille, is the name of his guitar. B.B. King. Well, was. I guess it still is. I mean, he passed away. But anyway, they also has a weird tone circuit. There's a little switch thing in there. It's got different. I'm not even sure what it does, to tell you the truth. But it was supposedly really great back in the day. But there's also a good rock guitar, right? There's a number of rock and rollers that play these. Oasis. That might be a band that maybe some of you have heard before. He always played I think he plays an Epiphone though, which is a cheaper version. This is usually a pretty expensive guitar, but I bought it used and I have abused it. Clapton played these often in a lot of different bands. He's awesome. He's almost kind of like more known for a Strat now, but. I gotta get that more fluted there. I kind of like they call the Clapton tone a woman tone, and I think the neck pickup does a little bit better job of it. Woman in a bad sense. They mean it's like that. It's just like, oh man, that is just perfect. It's like yeah, that's just a perfect tone. Actually, I never even thought about it. It's a compliment. Beautiful, great guitar. Love that guitar. Makes me very, very happy. So there you go. Another video in the can.